All right. Okay, good afternoon, everyone.
Hi.
All right, I like to hear that. All right, how are you guys doing today? Good? Okay, nice. Good to know you guys are in the zone. All right, so I'm sure most of you guys know what Data Science Club already, right? What we're about, but in case you guys, it's your first time coming to an event, Data Science Club is a club that hosts events such as workshops. We have reading groups and socials. Our main goal is to promote data science in the Waterloo community. And we also just want to provide you guys with something like this, accessible education for data science and like similar related fields. Okay, let's get into it. How do we, okay. Upcoming DSC events. Oh, they were supposed to be, okay, it's fine. So we have a food treasure hunt. Yeah, that's happening on June 28th. If you guys want more free food, we have some, I heard there's going to be like a lot of free food there. So who likes free food? Okay, I should have seen all the hands, but all right. Our most like soon event, I guess, is the Attention is All You Need anniversary, and it's also going to be a combination of a Cohere workshop and more prizes. How does that sound, guys? Yeah, yeah. Come on, let's hear it. Yeah, awesome. I like to hear that. And who's gonna show up? Okay. I like that. All right, that's it for me. You guys can keep an eye out for more of our events on our social media and our website. I'm gonna pass it over to Ernest.
All right, sweet. Yeah, so basically my name's Ernest. I'm currently studying CSPBA. I'm in 2B, and I guess we'll just get right started. So basically for today, both of the problems are gonna be dynamic programming problems. So what I'm gonna do is I'm gonna kind of introduce dynamic programming first. I'm gonna tell you guys what it is, when you want to use it, and then I'll kind of like teach concepts about it using these two problems. So if that sounds good, I'll just introduce that right now. So basically dynamic programming, I'll just refer to it as DP from now on. It's a method we use to solve problems that usually has two of these characteristics. So firstly, it has overlapping subproblems. So what that means is you can kind of break down the problem into smaller problems. And oftentimes these smaller problems are calculated more than once. And again, I'll kind of like show how this how it's used in like the problems later. And as well, another thing that I might have is an optimal substructure. So what that means is it usually might be a maximizing problem or a minimizing problem, where we kind of want to find the maximum or minimum kind of solution. And basically the whole premise of dynamic programming is that we want to reuse previously calculated values to avoid duplicate calculations and kind of save time on our problem. And this kind of process is called memoization. And the whole premise again, so because we're using previously calculated values, a lot of our future decisions are going to be dependent on our earlier decisions. So that's kind of like a high level overview of how we want to use DP. And some problems that might have DP, they're usually going to either be one of two types. First, optimum value problems. So that's kind of like the min-max value problems I was talking about. And another type would be counting problems. So how many ways are there to do this? Or what are the number of possibilities to do something like that? And below, I just listed some possible prompts to kind of give you an idea of what these type of problems are. But again, like even though you see like these kind of like prompts, just because it's a max problem or a min problem, it doesn't mean it can be solved using DP. But what I'm going to introduce is kind of like a step-by-step kind of framework to see whether you can use DP on a problem. Do we have any questions so far? Or looking good? Okay, sweet. So this is kind of the framework I've made for solving DP problems. And basically the whole premise is first you want to solve the problem using a brute force solution. So that just means like the worst time complexity, like probably going through every single combination, trying to see either what the optimal solution is, or how, like, the counting problem, like how many of a certain thing there is. So once we have that brute force solution, what we want to do is we want to use it to motivate us to find 3 different things. And I'll explain what these 3 different things are in future slides. But basically what they are state, transition, and a base case. And basically these 3 things are going to be kind of like interrelated with each other. And using like these 3 things, if we can find these 3 things and the relationship between each other, we know for sure that's going to be a DP problem. And after we've found these 3 things, we can then implement the problem using either a top-down approach or a bottom-up approach. So far, so good. Yeah. All right. So I'm just gonna go through this kind of like framework step by step using Fibonacci first, and then we'll go from there. So here's the problem for Fibonacci. So basically, I'm sure you guys are aware of what Fibonacci numbers are. So it's a sequence where the first 2 numbers are going to be 0 and 1 if you start from 0. And basically, any number after that is going to be defined using this relationship. So f of n is equal to f of n minus 1 plus f of n minus 2. So f of 2 would be equal to f of 1 plus f of 0, which is equal to 1. And f of 3 would be f of 2 plus f of 1, which is 2, and so on and so forth. All right. Okay, so basically in terms of the brute force solution, what we can kind of see is that we can use recursion. So basically how we use recursion is we, if we go back to this equation over here, if our function returns f of n, what we can do is we can call that function on n minus 1, we can call on n minus 2, and then we can use those return values to find our f of n. And for our recursion, we want to have a base case, which is f of 0 and f of 1. Is everyone clear on this so far, or do you guys want me to code this up, the brute force solution? So far, so good. Okay. And so basically what you kind of can imagine is that, let's say we're calling Fibonacci on 5. What we want to do is we want to call Fibonacci on 4 and 3. And when we call on 4 and 3, we call on 3 and 2, and so on and so forth until we reach our base cases here. So for example, let's say we're at the bottom here, we have Fibonacci 1 and 0. This returns 1 and 0 respectively. And we add those up together to get 1, which is Fibonacci 2. Again, we add these up to get Fibonacci 3, so on and so forth. So these are all just recursive calls to kind of get our final value for Fibonacci 5. And again, the relationship is defined using this formula over here. So in terms of how this relates to DP, what we can first notice is that we have a lot of overlapping subproblems. So in terms of subproblems, we're breaking this down into different kind of like subproblems over here where we have a smaller number, Fibonacci 4 and Fibonacci 3. Those are the subproblems we want to solve to get Fibonacci 5. And we also notice that there's a lot of these subproblems are overlapping. So we can see here, like we're calling Fibonacci 3 2 times, we're calling Fibonacci 2 3 times, Fibonacci 1 a lot more times, and Fibonacci 0 a lot more times as well. So what we can kind of imagine is basically we're duplicating a lot of calculations, and we really don't need to be doing that because, as I said before, we can reuse things that we've already calculated. So in terms of how we solve using DP, so let's go back to these 3 things: state, transition, and base case. I'm going to define them one by one in terms of this problem specifically. So in terms of state, basically what state is, it's going to be an array. And the array is going to have each of the sub-problem values memoized. That's the term for memoization, memoized. And basically for this problem, it's going to be a one-dimensional array. We'll call it DP. And DP of I is going to be the ith Fibonacci number. So for example, DP of 0 would be 0. DP of 1 would be 1. DP of 2 would be 2. So basically DP of I would also, you could also define it as the return value of the function Fibonacci I. And in terms of our transition, that's how, so as I previously said, our future decisions are going to be based off our earlier decisions. So our transition is how we generate one state from previous states. And in this problem, what this is this formula over here. Your transition is going to be a formula or it could be a series of steps you need to generate your next I value. And in this problem, it's going to be simple. It's going to be dp of I equals dp I minus 1. Sorry, this should be I minus 2 over here. I minus 1 plus I minus 2. And how I got that was I got it from our formula here, where f of n is equal to f of n minus 1 plus f of n minus 2. Does that make sense so far? Okay. And finally, we have our base case. So as you can imagine, if we're using our transition, eventually we want to kind of like reach some sort of base case, or we're just going to be recursing infinitely. And for here, our base case is going to be dp of 1 is equal to 1 and dp of 2 is equal to 1. Does that make sense to everyone? So what we've noticed is that if we have the base case and we use a transition to generate more and more states, what we can do is we can generate the state all the way up to n using this formula. All right, so now that we have these three things, we can approach this in two different ways. The first way is called a top-down approach. And what that is we're going to use recursion and memoization together. So we're going to be doing what we did before with recursion. So we're going to do Fibonacci 4 is equal to Fibonacci 5 is equal to Fibonacci 4 plus Fibonacci 3. But now, anytime we encounter a value that we've already calculated, what we're going to do is we're going to return that value instead of recursing. So I'm just going to put that in code right now. So basically, let me copy and paste a function. Oh, yeah. Is that big enough? Do you want it bigger? Oh, wait, never mind. Just saw how small it was. Okay. Let me close the. Okay. So basically, we want a Fibonacci. Let's just mimic what they give us on LeetCode. So on LeetCode, we have a class solution. And then inside the class, we have a function Fibonacci that takes in n, which is an integer, and returns n, an integer. So basically what we first want to do is we want to have our base cases. So basically in terms of the state, we can either store it in an array or in a map. So for this problem, I'll just use it. I'll just use a map. So here we'll just put our base cases at the very start. 0 is going to be 0, 1 is going to be 1, 2 is going to be 1. Those are our base cases. And when we recurse, what we want to do is we first want to see if n is already in the memoization or in the DP map. And if that's the case, then we don't have to recurse after that, right? We can just return what's in the map. If n is in self.dp, then we just return the value in dp. So far, so good. And then if that isn't there, so if that isn't there, then what we want to do is our transition. Our transition. And what we found before was that self.dp of n is equal to Fibonacci of n minus 1 plus self.fib n minus 2. And we just want to return the value we just calculated. So this is what we call a top-down approach, because what we're doing is we're starting from n and we're going all the way down to our base cases, which are 0, 1, and 2. I personally don't like a top-down approach. I think it's like harder to kind of visualize. So what I usually go for is actually something called a bottoms-up approach. So instead of using recursion, what we're going to use is an iterative approach to build the table. And what we're going to use for that is a for loop. So if we go back here, is everyone good with this so far? Yeah. All right. So in terms of the bottom-up approach, what we want to do is let's initialize a array. Let's just do this. And then what we want to do is put our base cases in. So dp of 0 is equal to 1. Sorry, it's equal to 0. dp of 1 is equal to 1. And then for I in range of 2 all the way to n plus 1. So we want to loop from 2 to n plus 1 because we've already calculated our base cases 0 and 1. What we want to do is dp of I is equal to dp of I minus 1 plus dp of I minus 2. And then we just return dp of I. So as opposed to a top-down approach, the bottom-up approach, we start from our base cases and we move up all the way to n. And I think this is kind of like a little bit easier to understand in terms of this. This is our transition. This is our transition. Base cases are over here. And then finally, we have our state defined here. Oh, sorry, this should be n. That look good to everyone? All right, so in terms of time complexity, what we've done was before when we used our kind of brute force solution, we look over at this chart, we'll notice that basically this chart is gonna grow exponentially. So the time complexity of this is actually gonna be 2 to the n. So our brute force solution is gonna be 2 to the n. But now once we've used DP, we've made it so that we can figure out the answer in O of n, because what we're doing is we're just looping from 0 to n, and we're only doing one calculation for each n. So that's going to be an O of n time complexity. All right. So now that we kind of know the basics of DP, we can apply this to a new problem over here, house robber. I'm just going to pull it up on LeetCode just because there's kind of like a diagram and everything. I think it'll be easier on that. Yeah. Okay. So basically, this is a problem house robber. So you're going to be robbing houses on a street. Each house has an. Oh, sorry. Let me zoom in for you guys. Oh yeah. Okay. So basically, you're gonna be robbing houses on a street. Each house has a certain amount of money stashed, and all these houses are interconnected. So basically, you can't rob two houses in a row, or else like the police will be contacted. And basically, that's just a rule. You can't rob two houses in a row. And what you want to do is you want to find the maximum amount of money you can rob on the whole street without alerting the police. So what that means is you aren't robbing two adjacent houses. So let me just plug in my laptop real quick. Yeah, but in the meantime, you guys can read through the example, see if it makes sense. Yeah, so basically, if we go through the example, basically the best way to rob this street is we want to rob the first house and the third house, because that would give us an output of 4, which is the maximum amount of money we can get. And over here, 27931, we can rob house 1, 3, and 5 to get our maximum output, which is 12. So basically, again, we're going to use the same framework, and instead of doing it, minimize this. So we're going to use the same framework we had from before. Ignore the state transition and base case for now. I'll go through that separately. But basically, again, first we want to write a brute force solution. Then we want to find our state transition base case for the DP problem. And then finally, we want to implement using a top-down or bottom-up approach. So I'm just going to open this up on a coder pad, and I'm just going to go through it step by step. So in terms of A. Okay, so in terms of a brute force solution, what we can kind of imagine is that we can basically check every single combination of houses that's possible and store how much we can steal. So for example, if we have 3 houses, we can steal from house 1, we can steal from house 1 and 3, we can steal from house 2, we can steal from house 3. And what we'll notice is that when our list is n long, there's going to be n factorial amount of those combinations. So that's kind of our brute force solution. Obviously, we don't want something that's O(n) of factorial. That's going to be really inefficient. So what we can kind of think of now is, okay, this could be a DP problem because we're trying to maximize something. And now we're trying to think, okay, since this is a DP problem, we want to find our state, transition, and base case. So let's write these out as comments right now. State comment, state, base, state, transition, and base case. So first, we kind of want to think, how can we represent this problem using an array? Does anyone have any ideas? Anyone? Okay. So basically, in terms of the state, what we want to do is we want to have a one-dimensional array, and it's going to be the same length as nums. It's going to be nums plus 1 actually, and basically dp of I will represent the maximum we can steal if there are only I houses. So for example, let's say we have dp of I, dp of 1. That's going to be the maximum we can steal if there's only one house. And the obvious choice there is that we're just going to steal from the first house. dp of 2 would be the maximum we can steal if there are 2 houses. dp of 3 would be 3 houses, and so on and so forth. So basically, the whole premise here is we want to find an array or a 2D array or any multi-dimensional array that can kind of represent the state of the problem. And one of these states should be our final answer. So in this case, dp of n would be our final answer, because that would tell us where n is the length of nums, because that would tell us what the maximum amount of money is, the maximum amount of money we can rob from n houses. So let's define that right now. So we're gonna make an empty array, and we're gonna make it this length of nums plus 1. And now we want to think how we can relate these states together. So basically, what we want to imagine is, let's say we know the maximum we can. So we know the maximum we can steal from the first house when there's only one house. So let's say dp of 1 is 2. dp of 2. We go copy and paste the example from before, actually. Okay, so over here, we have, this is our example over here. So let's say we have this example. So the maximum we can steal from, if there's only one house, is going to be 1. The maximum we can steal if there's only 2 houses is going to be 2, because we can avoid the first house and steal from the second house. And the maximum we can steal from if there's only 3 houses, would be 1 and 3. So I'm just going to write out all the states to kind of like motivate us towards the transition. So that's going to be 4, because we can steal from house 1 and house 3. And finally, the maximum, if there are 4 houses, is still going to be 4. That's the maximum. So some things we can notice is that, firstly, just because we have 4 houses, that doesn't mean we're going to steal from the 4th house exactly. That just means that we have 4 possible houses we can steal from. And we can also notice that the maximums from previous values can help us calculate the maximums from our next values. So what we also notice is that basically in our problem, one relationship that we're told is that we can't steal from 2 houses in a row. But other than that, we have no restrictions. So using all of this information, we can kind of think, okay, how does dp of 3 relate to dp of 2, dp of 1, and any of the dp values before? And what we notice is that dp of 3, basically dp of 3 here, we chose 3. And since we chose 3, we can't use 2, but we can use any values before 2. dp of 4, since we can either choose 4, so we choose 1, but we can't choose 3, or we can choose to not choose 1, and we can choose 3, because we can't choose 3 and 1 at the same time. So what we can kind of notice is that we have 2 situations. So either choose the current house, or don't choose our current house. So when we choose our current house, what we'll notice is that, so we're going to include the current value, so nums of I. And we also want to add the maximum value excluding the previous house, because we're not allowed to choose the previous house because we can't choose 2 adjacent houses. So what that means is we're going to add dp of I minus 2. So basically, this is the maximum of all the houses ignoring the previous house. If, let's say this is I, this is going to be I minus 1, this is going to be I minus 2. But in the case where we don't choose the current house, we can use any of the houses that, we can basically use any of the houses. And here we'll just do dp of I. Because dp of I is going to be the maximum of all the previous houses. And if we don't choose this house, the maximum of all the previous houses is going to be the same as the maximum of like all the houses, because we're ignoring it anyway. So it's going to be the same value. So here we have 2 situations. We choose the current house, or we don't choose the current house. And what we want to do is we want to find the maximum of these 2, and we'll store that as our dp. So for example, now let's apply this to what we have here. We're going to ignore dp of 1, just because that's going to be our base case. But we'll start off with dp of 3. So dp of 3, we can either choose the current house, which means we're going to have nums I, which is 3, plus dp I minus 2, which is dp of 1, which is 1, which here is going to be 4. Or we can choose to not choose the current house. And if we don't choose the current house, we want dp of I minus 1. And that is going to be dp of 2, which is 2. And what we realize is that we have a higher value when we choose the current house. So that's why we're going to choose this value. We're going to choose 4. Now let's try this for dp of 4. If we choose the current house, what we are going to get is nums I, which is nums 4, 1, plus dp I minus 2, which is 2. So we're going to get 3. If we don't choose the current house, what we're going to get is dp of 4 minus 1, which is dp of 3, which is 4. So our maximum value between these 2 is 4. So in this case, we don't want to choose the current house. Does that make sense so far? Questions? Yeah.
Why, when you don't choose the current house, it goes to dp of I minus 1, like not anything else?
Yeah, so basically, so let's say we're looking at this array. Not choosing the current house means we ignore this house being there. So could you say that, let's say we're on dp of 4. We want to ignore the 4th house. Is that the same as solving the problem if we only had 1, 2, and 3?
Yeah.
So if that's the same, then we know that dp of I minus 1 actually represents this problem, because it's all the houses up to the I minus 1 house.
Okay.
Make sense?
Yeah.
Right. Yeah. Oh, well, I first got them just by like doing brute force. Like I tried all the combinations. But here, after that, I kind of verified it using like our new solution where we either choose the current house or we don't choose the current house. I mean, like if we try all the combinations, so like we get basically what you can do is you can try all the possible combinations and you'll realize that the maximum value is 4. That's kind of like, yeah. So that's like that's kind of why we want to do the brute force solution first, so that we can do it ourselves on paper to kind of see what our values are for DP. And that way we can kind of motivate ourselves towards this solution and also verify our solution. All right, any more questions? All right, okay. So that's kind of our transition. So to formalize our transition, dp of I is going to be the maximum of dp I minus 1 and dp, sorry, and this formula over here. So this is going to be our transition. Okay. And finally, we want to do our base case, and our base case is going to be a little simpler here. So there's 2 ways to approach this. What we can do is we set dp of 0 is equal to 0. That's gonna be our first base case. So what this means is if we choose 0 houses, what's the maximum we can steal? And that's gonna be 0. And we also want to do dp of 1. I'll explain why later, but we also want to do dp of 1. And the maximum we can steal if there's only 1 house is the value of the first house. So in terms of the base cases, the reason why I chose 0 and 1 is because in our transition, we require I minus 1 and I minus 2. So basically, we can't use our transition to find dp of 1 because we're going to get an out of bounds error because 1 minus 2 is going to be -1. So we want to come up with base cases up until a point where we can start using our transition. And again, in terms of how I found the transition, I just did it using our brute force approach, which is try all the possible solutions and find out what the optimal value is. So for our base case, we're going to want to use our brute force solution to find the values. And we want to, again, find values up until we can start using our transition. Okay. And yeah, so I'm just gonna delete all the unnecessary things we have right now. So we have our state, our transition, and our base case. And what I'm gonna do is I'm gonna use a bottom-up approach because I think that's a little simpler. So we can actually uncomment this because this is actual code. So we have our base case over here. One, sorry. So we've set up our state. We set up our base cases, and finally we want to iterate. So let's see. All we want to do is for I in range of 1 to the length of nums. What we want to do is dp of I plus 1. Actually, I'll keep it to I. So let's start on 2. So that num lines plus 1. So dp of I is equal to the maximum of dp I minus 1, dp I minus 2 plus nums I. And that's going to be from our transition that we found earlier. And finally, we just want this is for that. And finally, we just want to return dp of length of nums because this value is the maximum number we can steal when we have length of num houses. All right. Do you have any questions? Yep.
For the base case with dp of 1,
yeah.
That's just when there's 1 house, right?
Yeah.
So like, why do you grab the 1 index of nums? Why
Yeah.
don't you just be like the first index would be 0?
Oh yeah, it starts on 0. That is my bad. It should be 0. Yeah.
You mentioned something about like top down and bottom up.
Mm.
So how do you tell the difference between the two approaches?
Yeah, honestly, it's usually personal preference. Bottom up, again, is when you go from the base case and then you kind of use a for loop or any other form of iteration, so that might be a while loop, to build up the cases until you have your desired answer. On the other hand, a top-down approach is when you use a recursive function. You start from the desired answer you want, and you recurse all the way down to your base case. I would say try to stick with bottom up for most of the things you're doing, unless you've already coded out your brute force solution and you use recursion for that. Then it's easy to kind of like add one line to kind of solve it using top down. All right. So yeah, so before we said that our time complexity would be n factorial, but using DP, we can kind of see how we've lowered the time complexity to O of n, because now what we're doing is, again, we're just looping from 0 to the length of nums, which is going to make it O of n. All right. Okay. Any other questions? All right, sweet. Yeah, that's basically it. I don't have really a formal conclusion. Here's kind of like a TLDR of what we just did in terms of the house robbers problem. But yeah, thanks.